Let's start once more from the hydrogen atom, and this time we want to study what happens when we add the effect of spin-orbit coupling. So what's that? That means we take into account an additional degree of freedom of the electron. The electron is a so-called spin 1/2 particle, whatever that is. And the first effect is that the Hilbert space, which was L2 of R3 for the hydrogen atom without spin over here, would now be L2 of R3 tensor C2. We already learned that spin 1/2 particles are described in space C2, and now for the whole system we need this tensor product here. And in the next step we will then introduce a Hamiltonian here for this spin orbit coupled hydrogen atom, which will couple the two factors. But before we do this, let's analyze the original Hamiltonian here, kind of embedded here in this space. So we would say, before we add a spin orbit coupling term, the Hamiltonian is just the original Hamiltonian tensor the identity on C2. And now what happens from a representation theory point of view? We know that the energies here, the eigenenergies of this Hamiltonian, they come in multiplets, they are degenerate, and the multiplicities are determined by, let's say, some irreps of O3. We said there are 2L plus one-dimensional irreps of O3. Actually, there was an even higher, there was an even higher symmetry, but let's forget about this. We know that we can group them in O3 irreps. And now from the C2 part here, for the spin 1/2, we also already saw in some exercises that there is an SU2 representation playing a role. Actually, the so-called defining representation, a two-dimensional representation of SU2. And now the thing that's interesting here will be this tensor product, but of course this kind of doesn't make sense at the moment, because we wrote these tensor products here for irreps of the same group, but now I wrote different groups down here. Well, actually what's going on here, and I'll be a bit sketchy, is that this O3 that incorporates rotations and reflections, and when we think about only the rotations, then we would speak about SO3. So actually there are SO3 irreps here, these 2L plus one-dimensional irreps. We can also view them as this. And now there is a relation between these groups SO3 and SU2, which we will learn about a lot more in a few weeks. And it turns out that in the end, if something is rotationally symmetric in quantum mechanics, what we really need are representations of SU2. So there is a way to view this here as an SU2 representation, and then we have also an SU2 representation here, and then it makes sense to speak about these tensor products here as a product representation now of SU2.